Welcome everyone to this lecture where we're going to discuss the motivation and history behind the idea of boosting. And keep in mind that the concept of boosting is not actually a machine learning algorithm. Instead, you can think of it as a methodology applied to an already existing machine learning algorithm. However, it's most commonly applied to the decision tree because that's where it yields the best results. And so often boosting is actually referred to as meta-learning instead of machine learning, because really it's a process where you decide to insert any machine learning algorithm. So let's actually explore this idea by reviewing a simple application and formula, which we're going to go into a lot more detail when we talk about adaptive boosting. Now, the main formula for boosting looks like this, where you say that your overall boosted meta-learning model is equal to the sum of t number of models. And what does that actually mean? Well, when we talk about boosting, we're typically referring to the process of aggregating a bunch of what we call weak learners into an overall strong ensemble model, which means we can think of this lowercase f of t of x as some coefficient times a machine learning model. So it implies that a combination of estimators with an applied coefficient to each specific estimator could act as an effective ensemble estimator. We can imagine that h of x is the results of a specific machine learning algorithm. And the reason we call it h of x is because we think of this as a hypothesis. So we have an estimator coming up with its own hypothesis of what the output should be, either trying to predict a classification or regression, and then we take that specific model and multiply it by some sort of coefficient. And we do this for a bunch of different varieties of that model. And then we can sum that all up into an ensemble. And this is the idea behind boosting, specifically adaptive boosting. And we'll see later on how gradient boosting also builds up on this idea. So keep in mind that h of x in this particular instance can actually be any machine learning algorithm. That is, it can be any estimator or learner. Typically, you pretty much always see it as a decision tree because it ends up working really well for decision trees. And you'll also notice that if you begin to apply this boosting formula for other models, it will actually eventually resolve into another version of that machine learning model. So you can imagine that if this was done for linear regression, this actually looks extremely similar to linear regression, where instead of a beta coefficient times a particular feature, you end up getting this alpha coefficient times a weak learner or a hypothesis function. So if you were to try this with something like linear regression, it would actually resolve to multivariate regression. So you can check that out online as well, as far as boosting linear regression and how that could resolve into a multivariate regression. And later on we'll see why this is so ideal for decision trees and why pretty much whenever someone is talking about boosting, they're usually talking about a machine learning method based off the decision tree model. Now, the question we want to really answer with boosting is, can an ensemble of weak learners, that is, very simple models, so when I say the term weak learners, I'm just talking about the simplest version of a model possible, and can an ensemble of those weak learners that are slightly different, and then we multiply them by some sort of coefficient and sum them all up to get an ensemble, can those together be a strong learner when we combine them in this sort of way? So for decision tree models, we can use simple decision trees in place of h of x and combine them with the coefficients on each model. And later on, we'll discuss this by thinking about what the simplest decision tree possible is. And we'll discover it's actually just a stump where you have one root node and two leaves, and that's it. No further leaves going down. And we'll talk about that in a lot more detail when we walk through the process of adaptive boosting in the next lecture. Now let's talk a little bit about the history of boosting. The idea of gradient boosting originated from Leo Breiman when he observed that boosting can be interpreted as actually an optimization algorithm on top of a cost function. And he published this in the late 1990s. And later on, other research by Jerome Friedman and many others developed more explicit formulations for gradient boosting. And it should also be pointed out that in around the same time frame, 1990s, that two other researchers developed the adaptive boosting algorithm, which again also combines weak learners in ensemble to create a stronger model. So the whole idea behind boosting is, can I take a bunch of weak learners that is very simple models and then combine them together intelligently in order to create an overall very strong estimator? And this idea of the ensemble is very similar to what we've seen for something like random forest. Can I take this variety of models and then use the combination that is the ensemble in order to create a very strong model? Now, random forest had its own techniques for separating out those different models, and we'll see how boosting is kind of this meta technique that you could technically insert any machine learning algorithm into. So what we're going to do is we're really going to focus on understanding the theory behind this by first learning about adaptive boosting, or AdaBoost. Now this is the simpler of the two to understand, and building an understanding on that, on how to combine those weak learners to create a strong estimator, will paint a really clear picture of what boosting is. And we're also going to be exploring why decision trees are so well suited for boosting, which is why pretty much when someone's talking about boosting, they're really talking about boosted decision trees and not boosted other machine learning models. Okay, let's get started. I'll see you at the next lecture.